Welcome virtually to Brookhaven National Laboratory. I'm Bob Gordon, and I manage the U.S. Department of Energy's office here at B&L. Before you begin exploring this amazing place, let me tell you about the Department of Energy, Brookhaven's owner. The Department of Energy's Office of Science provides most of the lab's $700 million annual budget. We've hired Brookhaven Science Associates, a partnership between Stony Brook University and Battelle Memorial Institute, to run our laboratory, and especially the conduct of world-class science. You probably didn't know that the Office of Science is a world-leading supporter of research in the fundamental sciences. Battelle and Stony Brook are both leaders in science, education, and research. Together, we strive to realize the DOE mission to ensure security and prosperity through transformative science and technology solutions. And you're part of it. Welcome to B&L Summer Sundays and enjoy the visit.
Hi, and welcome to the United States Department of Energy's Brookhaven National Laboratory. Thanks for joining us virtually as we share our groundbreaking research and unique facilities with you online. Today we're going to take you to the Relativistic Heavy Ion Collider, or RHIC, a one-of-a-kind physics facility funded by the Department of Energy's Office of Science. Physicists from around the world come here to study what the universe may have looked like in the first few microseconds after the Big Bang. We look forward to seeing you in person in the future, but for now, your tour guide is ready to show you around.
Thank you, Kahil. Hi, my name is Will. We're here at the Relativistic Heavy Ion Collider, or RHIC for short. It's an amazing machine that allows scientists to see what atoms are made up of. We know that atoms make up all the matter around us, but there's still much to learn about what makes up atoms. RHIC takes atoms without their electrons, now called ions, and smashes them into each other to find out what's inside. Scientists study these ion collisions to learn what the early universe was like and how atoms make up all the matter we see in the universe today. RHIC collides two beams of ions head-on while they're traveling at close to the speed of light. The particles actually start their travel far from the collider and travel through a couple of smaller accelerators. They get faster and faster until they are injected into RHIC, where the beams of ions go in opposite directions around the larger ring. At top speed, the ions can circulate in RHIC for up to 24 hours. For most experiments, RHIC uses ions of gold, but it can also collide other types of ions too. It can also use single polarized protons, which is important for understanding proton spin, a property used in MRI scans, but something that scientists don't fully understand yet. Results from RHIC experiments show that the early universe was like super hot soup of matter. This matter is called the quark-gluon plasma, and it's about 250,000 times hotter than the center of the sun. Special magnets called superconducting magnets steer the ions traveling around the ring. Let's go take a look at one. Here we have one of the RHIC magnets. There are 1,740 of these throughout RHIC. Ions travel through the beam pipe at the center of these superconducting magnets, which have to be kept very, very cold. These are chilled by 25 tons of helium to reach negative 452 degrees Fahrenheit. That's almost as cold as anything can get, around 4.5 Kelvin. Inside this magnet, you see a cross-section of the beam pipe where the ions travel. The beam pipe is kept under vacuum, so that way there's no other way particles or gases can interfere with the particles that the scientists want to see collide. It's also surrounded by coils of superconducting wire that can conduct lots of electricity without losing energy, and that allows the magnets to carry large current and create a very strong magnetic field to steer the ions around the RHIC ring. The superconducting wires are surrounded by insulation, and there's also space for the helium to get piped in and out to keep everything very, very cold. So let's see where the super cold liquid helium is pumped into RHIC's magnets. Come on, let's go. Now we're inside one of the largest single refrigeration plants in the world. Just like your home refrigerator keeps your food cold, this refrigeration room keeps the RHIC magnets cold and superconducting. Both systems use a chilled liquid to take away the heat. At RHIC we use super cold liquid helium. The helium to cool the magnets is stored in 47 large tanks. Cold helium gets pumped through the magnets that make up the two RHIC rings and takes away heat from them to keep them cold. Then it returns it to the refrigeration room warmer than before, and 26 compressors make it super cold again. The heat that's removed in this part of the process goes to the cooling tower, and the rechilled helium is sent back to cool the magnets even further. Directly underneath this building is the collider tunnel where the particles speed around in the magnet rings. To get collisions, RHIC is two accelerators in one. Each one is made up of those long superconducting magnets strung end to end like beads on a necklace. At various places around the ring, physicists steer both beams into a single beam pipe so the particle beams can collide. Huge detectors surround this interaction area and record signals that tell what kind of particles come out of the ion collisions. The signals that the detectors pick up provide physicists with information about the conditions created in the particle collisions. Let's go look at where one of those detectors is located. Here we're at RHIC star experiment. Behind me is the shield blocks, and behind the shield blocks is a 1,200-ton magnet detector for STAR's experiments. It's about as large as a 3-story house. STAR specializes in tracking the thousands of particles produced by each ion collision in RHIC. It looks for signatures of that quark-gluon plasma. RHIC detectors have picked up signals that tell us not only is super hot quark-gluon plasma created during the ion collisions, but that matter also has no viscosity or resistance to flow. It is technically a perfect liquid. Scientists have also observed that gluons play an important role in proton spin. Another large detector, Phoenix, is now being transformed into a new detector named S-Phoenix. It will be able to study some of the most intriguing particles that are created in RHIC collisions. Nuclear theorists continually refine their calculations to help make sense of the data and compare the experimental results with physicists' expectations. But there are still many questions about the nature of this matter, and S-Phoenix will help answer them. So here we are in the building with the main control room. Behind me is a mural of one of the smaller accelerators, the AGS, Alternating Gradient Synchrotron. Operators such as myself make sure that all of these smaller accelerators and systems are running correctly, and from here, physicists can also steer particles to facilities that explore the effects of space radiation, so we can help protect future astronauts, and to make important isotopes for diagnosing and treating diseases like cancer. All of these programs will continue to move forward as RHIC begins to finish up its experimental program. In the near future, a major collaborative effort will transform some of RHIC's components into a brand new nuclear physics research facility, an electron-ion collider, or as we like to call it, the EIC. It will be two intersecting accelerators, one with a beam of electrons, the other with a beam of protons or heavy ions. It will be able to produce three-dimensional snapshots of the internal structure of the protons and ions. Like RHIC, the EIC will be funded by the federal government through the Department of Energy's Office of Science and will draw on expertise from throughout the DOE National Laboratory Complex and at universities and research institutions around the world. EIC partners will include the Thomas Jefferson National Accelerator Facility, Jefferson Lab, in Newport News, Virginia, as well as nearby Stony Brook University and other international participants. We look forward to serving the worldwide EIC user community, already more than 1,000 scientists from 30 nations. We hope you'll come back to learn more about our progress and discoveries as we enter this next frontier. So thanks for joining us on this tour of the RHIC complex. Back to you, Kahil.
Thanks, Will. Now that you've seen what's inside, you might have some questions. So we've gathered a group of experts who work at RHIC and we'll be streaming them to you starting now. This is a live online discussion, so be sure to join in and ask your questions. Enjoy!
Thank you, Kahil and Will, for the awesome introduction to the RHIC facility. A big hello and welcome to all of you who have come to attend our RHIC Virtual Summer Sunday this year. My name is Gene Van Buren. I'm a nuclear physicist here at Brookhaven National Laboratory and who specializes on computing aspects of the data we collect. I say here, but today I'm coming to you from my son's illustrious, or rather illustrated bedroom. RHIC facility and the experiment that's there are actually running right now. You wouldn't get to see as much as we'd like you to see if you were there anyway. But anyhow, today we're working virtually from wherever we are. I've been able to participate in many of the Summer Sunday open houses that we've had for RHIC over the years, and fortunate to meet many people who have come and visited us over those years. And while I greatly appreciate the chance to interact directly with the visitors who come, I'm also glad that this year's virtual open house is making it possible for people from just about anywhere to join us. So welcome both to the people from the Long Island area and people from far beyond. Thanks for joining, and we're glad to have you here today. Brookhaven National Laboratory itself is also similarly a place that involves people from the local area and from the far corners of the U.S. and the world. Today we'll have a chance to meet a few of those people, and I'd like to take this time to have them introduce themselves as I have myself. We're going to do this with a little bit of a game. It's a true or false game, and you're all welcome to play along at home. So I'll read to you a couple possible truths about each person in our panel of scientists, but only one of the two things I read will be true. Take your guess and listen in as the person explains a bit about themselves and which is true. I'll also start by saying thank you to the members of our panel for their willingness to come and give some of their time and share some of their knowledge with us. That is much appreciated. All right, so moving forward, the first person I'd like to introduce is Angelica Drees. And let me give you two items that could be true about Angelica. So the first is that Angelica once trained and worked as a farrier. That's someone who shoes horses, as I understand. That was something new for me. That's one possibility. The other is that Angelica is fluent in Russian. So take it away.
Hello, Jean. Thank you for the introduction. It's good to see everybody today. And yes, the first thing was true. I actually have trained and worked as a farrier. This is one shoe that I didn't paint but make, a few years ago. When I was still doing that, when I was a student, students have to eat too, and I made my living as a farrier. And, about Russian, it came to my mind, I do speak several languages. I'm from Germany, so I speak fluently German, of course, English too. I hope you will agree with that statement. I also speak fluently French and a little bit of Russian. So just to say, hello, which is privyet in Russian, and a few more words, but very far from fluent. And I'm an accelerator physicist, and I actually originally am a high energy physicist working in experiments. So I'm a little bit, trained in both areas.
All right. Thanks, Angelica. Or danke. All right. Next on our list of panelists is Michiko Minty. So the two items that we have for Michiko are, one of which is true, is that Michiko likes to study and solve unsolved problems. Or Michiko likes a workday that ends at 5 p.m. Take it away, Michiko. You need to unmute.
Thanks for the intro. Yes, my name is Michiko Minty. I am also an accelerator physicist in the Collider Accelerator Department, and I'm present head of operations. And I have a background in nuclear physics, but gravitated toward accelerator physics during the early part of my career. I was attracted to physics actually by the influence of people in the dormitories that were fascinated with the field and talking about all sorts of puzzles that I, at the time, didn't understand. And soon afterwards, I started taking physics and learned that the world of physics can answer a lot of questions you have about nature and the universe. So I do like to study, and I do gravitate toward issues and problems that don't have solutions as something that I like to work on. And it is false that I like to end my work at 5 o'clock. I like to work when the time is right, and that often involves working at night and on the weekends. Thank you.
Yeah, that sounds like a number of us. Our work days tend to go a little bit, or a lot bit past 5 p.m. sometimes. All right, next up, our next panelist will be Prithvish Trivedi. The two possible items that might be true about Prithvish are that math was Prithvish's favorite subject in school, or Prithvish acted in a play during his college days.
Thank you, Jean, for the nice introduction. First of all, I need to say that I am very glad to be here. I wish we could do this in person like every other year. Anyway, so let me make a few remarks. I am a member of the collaboration that built and right now operate the STAR experiment at the Relativistic Heavy-Ion Collider. In fact, this year, in the month of June, STAR and also the Relativistic Heavy-Ion Collider celebrated 20 years of successful operation and scientific discovery. Personally, I have been a member of the STAR experiment into all these for last 10 years. Did my PhD, postdoctoral research, and now I am an assistant physicist at Brookhaven. So I study a very interesting aspect of heavy-ion collisions. When two ions collide, they produce a very strong magnetic field. In fact, it's the strongest in the universe. And I try to study what would be the observable consequence of that magnetic field. So now about the two statements. The true statement is that I did actually act in a play when I was in college. It was a comedy drama. I think some of my friends must have put it on YouTube. It must be somewhere, I'm pretty sure. And in fact, I have been doing this ever since I was in my elementary school. My mom is a playwright, so she would write something, would give me a role. And math wasn't my favorite subject in school. Bioscience was. In fact, I did struggle sometimes doing math, but I gradually acquired my interest in math and also in physics when I went to college. So thank you so much.
All right, thanks, Prithvish. We're going to have to find out what your views on math were if you didn't say so. Thank you. All right, next among our panelists is Christine Natras. Welcome, Christine. Christine has these two items to guess from for the possible truth. Christine has supervised over 30 undergraduates in her research since 2012. Or, when Christine teaches projectile motion, movement of objects, she throws a stuffed elephant at her students as a demonstration. All right, I'm curious to hear that.
All right. Thank you for the introduction. And I'm here today representing the S-Phoenix experiment, which is currently being built. It's a very exciting new experiment. So the first one is true. I have had 32 undergraduates, many of them in something called a course-based undergraduate research experience, but a lot of them working one-on-one. I love working with undergraduates, as well as my graduate students. The second one then is false. I do not throw a stuffed elephant at my students when I'm teaching projectile motion. I throw a stuffed warthog. Her name is Wanda. And she is currently on a leave of absence because of the pandemic, because it's not safe to throw a warthog around the room. But I have given her a research assistantship in my group.
Those students that you've had with your research, that's in addition to the students that you teach in classes as well, I guess.
Yes.
Wow.
Yes.
Great. All right. Thanks, Christine. All right. Next up on our panel is Alex Jensch. And Alex has these two possible truths. The first is that Alex plays guitar in a cover band and was planning to be a full-time musician before he decided instead to pursue a career in science. The alternative is that Alex has memorized all of the lines to every Monty Python movie ever made. Tell us, Alex, which is true?
So, hi, thanks, Gene. I'm Alex Yench. I have worked both in the STAR experiment, and now I'm working on the electron-ion collider, or the future electron-ion collider. And as it turns out, the first question, or the first response there is actually the true one. I actually do play in a cover band here on Long Island. Of course, the pandemic has made it a little bit hard to play anywhere at the moment, but I think the guitars in the background probably gave away the answer. I probably should have thought about that as a backdrop. And the second one is actually partially true. So I've memorized the lines to all the Monty Python movies that I have seen, which is most of them, but I think there are probably a few episodes of The Flying Circus that I have yet to see. But most of them I have memorized, which is very annoying to anybody who is friends with me, I think, at this point.
Thanks for being willing to admit a possible character flaw there. I don't know.
I have no problem with that.
All right. So thank you all for introducing yourselves. Let's move forward. Next thing I'd like to point out is that this is a live discussion with the ability for people to submit questions on social media. I believe we are streaming live on several platforms. So on whatever platform you're watching this, you are welcome to put in the comments a question and ask it, and we'll try to pick it up from the feed and see if we can have our panelists answer those questions. So please feel free to participate. While waiting for more questions to come in, we're going to start out with a little bit more true and false to get the questions going specific to the topic that we're discussing today. So the first true and false question I'll ask to our panelists is whether RHIC is both a particle accelerator and a particle collider. Is that true or is it false? Michiko, how about you answer this question?
Okay. The answer is that this is a true statement. As you've seen in the video, I hope, there are a number of accelerators that are used to bring the beams into the relativistic heavy ion collider. And once they're there, they are accelerated through the many superconducting magnets, which orient its trajectories, and accelerated to high energies using radio frequency cavities. In the video, you saw that there were actually two such accelerators. So RHIC consists of two superconducting accelerators, which with beams that travel in opposite directions and can collide in up to 6 points. We call these interaction points. The energies of the beam in the relativistic heavy ion collider are very high, and the speed of the particles is relativistic, as the name implies. So the circumference of RHIC, as you might have seen in the aerial view, it's about 2.5 miles, and that corresponds to particles traveling round and round in each of the accelerators about 80,000 times per second. That's what it means to be relativistic.
I wish I could run around the ring that fast. That's pretty fast. Thank you for the answer, Michiko. So in addition to the panelists answering the questions, if anybody on social media wants to take a guess, you're welcome to put true or false or T or F in the comments section, and we'll try to see if people generally get the questions true or false correct on their own. But next, let's move forward with another true or false question to our panel. So the next question I will ask is, when the ions collide in RHIC, an explosion occurs. Angelica.
So this is one of those questions you can answer yes and no. So it's actually no, in a way that what you think of an explosion, that would have rather big scale, like two cars, smashing into each other or something. So that's a no. However, if you are the size of what these particles are, yes, it actually is an explosion for them. So just to give you an idea of the sizes that we are talking about, I actually made a prop. We are all doing this for the first time, through a video feed. I don't know if you can see that here, so this is actually a hydrogen atom, with a proton in the middle and an electron here. And you see, the size of it is a 0 point, and then there are lots of zeros, 1 meter. So it's actually 10 of them. We call that orders of magnitude. So this is the size that we are talking about here. This is the order of 1 meter. This is Danny DeVito. And this is actually 1.4 billion meters. This is the size of the sun. So, so there are a lot of orders of magnitude, and we are really, talking about the smallest order here on that side. And if you translate that into the big world scale, the collision or the explosion would correspond to 2 angry mosquitoes, bumping into each other. So this is about the large scale of collision that we actually really deal with. In addition to that, it lasts a very, very, very short time, meaning it's only like a split second, or much less than 1 second, that these explosions last. But for the involved particle, the nucleus of a gold ion, which is what we collide mostly, or 2 protons, we have both at various times. They actually get destroyed in the process and form new matter, which I'm sure we're going to talk about a little bit more later. Thank you, Gene.
All right, thanks for the answer, and thanks for bringing along some props to show. I understand the mosquitoes must be angry. If they're not angry, it's not happening. All right, great. Our next true or false, again, feel free to answer in the social media comments if you like. The next true or false you can guess is the star detector, which is the experiment running right now at RHIC, takes just a single type of measurement from the ion collisions. What do you think? Is that true? Just one thing? You tell us, Prithwish.
Okay, so this is a true-false actually statement. So the answer to that is it's actually false. When collisions occur, like when the 2 ions collide, many different kinds of things come out of it. And our goal is to detect as many objects that we can measure, like as many objects that we can. This is to study actually what exactly happened in the collision. So STAR stands for Solenoidal Tracker at RHIC. It gets its name from the fact that it sits inside a big magnet, which has a solenoidal magnetic field. You can think of this as a big camera, which takes 3D images of whatever comes out of the collisions. Now, every camera has its limitations. My eyes are cameras, and you can see it has limitations. So, as of now, this detector has 7 major subsystems. Each specializes in detecting a specific kind of objects that come out. It could be a subatomic particles, which has charge. It could be just light, gamma rays, which has no charge. And we detect them, we try to count their numbers, measure the distribution, try to analyze the data from that. So that's the answer to the question.
All right, yeah, so very multi-purpose experiments. Good. All right, our next question will be about the stuff that we produce in the collision. So if you were watching the video earlier, you probably caught that they talked about quarks and gluons. So the question here, it's another true or false, is that RHIC creates a hot soup of particles called quarks and gluons that existed by themselves at the very beginning of the universe, some 14 billion years ago. True or false? Christine?
Thank you. So this one is true. So if you were able to look inside of protons and neutrons, you would see that they are made up of smaller particles called quarks and gluons. And what happens when we smash these nuclei, we get these nuclei moving very, very fast. The nuclei are made up of protons and neutrons themselves. We smash them together, and it very briefly melts. And so this is just like what you would get if you took two ice cubes in outer space and you slammed them into each other. The system would melt, and then it would expand and cool and refreeze. And we're basically reconstructing the properties of that matter by looking at those refrozen shards of nuclear matter. And when we first started doing this about 20 years ago, we thought that this was going to be a gas. Everybody expected it was going to be a gas. And what we learned over the course of our studies was that it is actually a liquid. And as you can imagine, when we were planning RHIC, which the planning actually started several decades before it even turned on, we didn't know what we would see. So we have learned a lot in the 20 years of RHIC running, and that's the motivation for building the S-Phoenix experiment, because we basically can now build a detector that can help answer questions that we weren't able to answer before. And we're really excited to get started soon.
I think it means we weren't even able to ask those questions, right? Because we didn't know what we know now. So
excellent point. Yeah,
that's great. Yeah.
Yeah. We had a few guesses about parts of it, but not everything. All right. Thank you. All right. Let's move to the fifth question I've got is fifth true or false. Again, feel free to guess. RHIC is the last step, the final step scientists need in their quest to understand matter and the universe. Alex.
So this is definitely false, and I'm actually very happy for that, because that means we have lots of work left to do. So we actually have a lot of things we still have left to learn from experiments branching in all different areas of physics. So not just in our particle accelerator experiments, but also in observations in astronomy and new types of particle collisions that haven't really been studied yet. So the goal of the electron-ion collider, which will start being built after RHIC has finished its experimental program, is to study collisions between electrons and ions to try and better understand what the ion actually looks like before we even start seeing these types of heavy ion collisions. So one of the challenges in trying to do this type of physics is you're essentially trying to learn about something by looking at the debris of its explosion. So imagine trying to understand a firecracker by taking all the flecks of paper and material after the thing has exploded. And you have to rebuild the firecracker from those pieces and understand what it was. Well, that's very challenging. So the electron-ion collider will give us an ability to actually look more carefully into what the ion looks like before the actual collisions really start taking place between like the heavy ions like we're doing now. And so we still are very far from having a complete picture of everything we see in nature. And so it's a very exciting time as we start to develop better tools and new types of experiments that we can use to really study this in more detail going forward.
All right. We'll check back in with you when you're much older, Alex. We'll see how far you've got. All right. So thank you each for those answers. Let's now turn to some of the questions that we've gotten from the social media feeds. So let's start out with the first question. Actually also mentions that electron-ion collider. How long do we expect the electron-ion collider that follows RHIC to be in use? And Christine, how about you take this?
So we don't know exactly, but we can say from if what you get if you look at historical colliders that were created, colliders and accelerators, is they don't really ever go out of commission. They just get recycled and put to some other use. So most of them are used primarily as cutting-edge research facilities for something on the order of 2 decades. But then after that, if you look, for instance, the alternating gradient synchrotron is what accelerates particles up to the speeds for injection for the relativistic heavy ion collider, and it was built in 1960 and it's still in use. So we keep finding new uses for these things.
That's right. The AGS is also even used for additional physics beyond feeding RHIC, as I understand. Great.
But the EIC is not going to be fed into by RHIC, right? It's actually going to be replacing RHIC in its own tunnel or using parts of it, actually, and building a new accelerator in the same space.
Yes, there will be the addition of the electron collision ring or the electron
Right.
accelerator inside the tunnel. So it's going to be making that tunnel very packed
Yes.
when we actually
It's gonna
build the
be
EIC in there. It's going to be a very
really
unique
busy.
engineering challenge.
In the olden days when RHIC was being built, we could take bicycles and ride around, which we did. At times when there were no experiments in the way. We won't be able to do that any longer because it's going to be too full.
But we can still ride our bicycles around the road.
Yes.
So the EIC itself will be an example of reuse, and I think that's a great way to put it. Thank you. All right, moving to the next question. This is from Stephanie on our Twitter feed. Stephanie would like to know more about the RF, or radio frequency, that's used in RHIC. Perhaps, Angelica, do you want to try to take this?
It's a funny phrase question, as in more, so I don't know who was asking and how they do know. So radio frequency cavities is a pretty fancy word, I would say. They are actually the accelerating devices, that actually bring the particles that we have in there up to the speed at which they collide eventually. People often think that actually the magnets are used to accelerate the beams. However, they are not. The magnets, we only need them to steer them on a circle. And the accelerating devices, the radio frequency cavities, they are the ones, bringing them up to speed actually by a factor 10. That within RHIC we accelerate the particles by another factor of 10. Up to very, very close to the speed of light, which, when we use the word relativistic, that's actually what all that means. It means something that has or is close to the speed of light. And as they go faster and faster, just imagine you're a car on a racetrack of 3.8 kilometers, going close to the speed of light. You really need very, very strong magnets to actually keep, yourself on that racetrack and not going, out, which of course also happens at times. So as the accelerating devices get, accelerate the particles more and more, the magnetic field has to become stronger and stronger and stronger to keep them on that circle. That all has to work together. We call that a ramp. So that's what makes our accelerator actually an accelerator, not only a collider. And we do that in parallel in the two rings, right? We have one clockwise, one counterclockwise. So we call them blue and yellow. It's, it's just that's the name. It could have been A and B or 1 and 2. Actually, going back to my little mosquitoes, if you could see, closely, they're actually the one here, this one is yellow and this one's actually blue. So it's actually really blue and yellow that are colliding here for clockwise and counterclockwise. So we have two sets of radio frequency cavities, one in each ring that work mostly independent of each other. I say mostly because they do have the same frequencies and all that, because the particles are supposed to collide, and that's actually very important. It's easy to miss, the other one if you are at the speed of light and only, a few, say 30 centimeters or so long, before you know it, the other one's already gone, but you have to actually meet at the center of the experiments. That's what we do with the radio frequency cavities, or short RF. We like shorts and abbreviation. Coming from Germany, that was really a challenge when I came first to the US, by the way. All these abbreviations, I said, whoa, slow down. What does all that mean? So,
Isn't there a really cool science fiction style name for the radio frequency cavities that's also used? Like klystron or something?
Well, there are also klystrons. Those are radio frequency. I mean, we have, basically they power them, if you like, so they get their power from something. They are thyrotrons and klystrons, so we have a lot of these, fancy named devices in there. That's true.
I appreciate the point you made, Angelica, about easy to miss. I know that the collider runs with not just a single ion colliding with another one. We throw a lot of them at each other, and almost all of them miss. Right.
Yeah, they don't really miss, as in we didn't manage to get them there. You know, they miss as in it's like two clouds that go through each other, and most of the components, you know, the individual ions actually do not collide. Every time they go through each other, more often than not, actually all of them go through each other and nothing happens. The denser we can pack the clouds, if you like, you know, with particles, the likelier it is that two of them actually collide. And that's what the experiments always want from us, more. It's like at home with children, you know, they always want more. So that's one of the challenges and things that we work on as accelerator physicists.
All right, let's take a question now from social media on what it is we collide. So this was a question asked by email. Why would you specifically use gold in RHIC? And I'm going to throw this one to Michiko.
So what kind of particles we collide? The relativistic heavy ion collider was designed to collide heavy ions. And in case the point was missed, we also can collide light ions and even down to protons. So I like to say that the relativistic heavy ion collider, compared to other colliders in the world, which there are not very many, is the champion of versatility. So we've collided protons on protons, gold on gold, which is a favorite from the quark gluon plasma perspective, and all the way up to uranium on uranium. In addition, we've actually, because we have the two independent superconducting rings, we are able to collide ions of different species. So we can collide light ions versus against heavy ions, and that is really a very unique feature that greatly allows to expand the science that's done at RHIC.
Now, one small point is that from the experiment's perspective, we don't care too much which heavy ion we're colliding. So my understanding, and Michiko can maybe expound upon this, but is that really we use gold because Brookhaven already had a gold source. CERN uses lead because they had a lead source. And for the quark gluon plasma in those studies, all we need is something large.
And here I am thinking you cared all those years, and now you're telling me you don't.
Well, there is one other point about the ion, too, and that's the actual shape of the nucleus. And so gold is good because it's nice and spherical. And so if we want to study something that depends on the initial shape, something that depends on the geometry of the collision, for instance, gold is good because we already know that it has a nice spherical shape, whereas uranium is kind of more oblong. It looks more like a football. And so for the uranium...
It's also readily available. You know,
yes.
And easy to have in a source, you know, and we've had rarer elements, you know, like rubidium and zirconium, you know, that they're just hard to come by to actually make sources of and accelerate them. So gold is just the easiest. And it sounds the sexiest, I always thought, you know, gold collisions, you know, it sounds better than uranium, I think.
Does anyone want to comment on whether we're destroying the U.S. supply of gold?
It's the total amount was less than a wedding band that we have actually, you know, I mean, abused in a way of that they don't exist anymore, right? Because we collided them and destroyed them in the process. So no, you know, rest assured, your gold reserve is still intact.
Whew. Good. All right. So the gold isn't the expensive part. Good.
No, it's us.
All right. Here's another question from YouTube. I'm going to send this one to Prithwish. How long is the time between the collisions of the data, collisions of the ions, the collection of the data, and then the analysis of the data? How long does all of that take?
Yeah, it's a good question, very good question. It actually depends. It can take from several months to maybe a couple of years. We collect data over many months, like the experiment can run for 6 months or so. We take collisions, we take data like about, let's say, 1,500 to 2,000 collisions per second. That's an enormous amount of data we collect, it goes temporarily to a computer server. The first thing we do is we look at the data and we try to calibrate the detectors. Some of the detectors might have some problems. We correct the data. Then we clean up the data. And then finally, it gets to a point where we do a mass production using a computer cluster, which takes several months. And then finally, it gets to the point where we can actually analyze, do a physics analysis. Physics analysis can also go for a very long time. And it doesn't stop there. Once you have the results, there would be lots and lots of debates. Some professor would tell you, oh, I don't agree with your explanation and things. So finally, it can take actually more than a year to publish a result. Even you are not done there when you get to give talks. So the whole process can take several years from the collection of data to actually publish an exciting result. I hope that answers the question.
And I think it's sometimes, even people go back and say, wait, haven't we had this in this data? And then they start to analyze something with a question that came up down the road, and then they go back. So I'm collaborating with somebody who's looking now at data from 2011 and 12. That was, of course, analyzed then too, but now they're going back and looking again. So I think the data sits there and is actually, often analyzed more than once, under different views and questions.
Right. And in fact, just to add that if there is really some problem or if we need more data, every year we write a document and ask for more money from the government so that we can do the experiment one more time, collect more data. We sometimes add a new detector. We want to again run the experiment, collect more data. So this keeps on going. And somebody gets a very bright idea. He wants to do a specific thing. We again go back and do the experiment. So it's been going on for last 20 years, as I mentioned before.
Yeah, indeed, I was asked to restore some data from 15 years ago now if somebody's doing some analysis. So indeed, new questions come up that the data that we have taken already can be used to answer, as well as new data that we might collect. Great. All right. The next question that we have is from YouTube as well, and the name is one that I'm not sure I could pronounce correctly, so Nkeru, something like that. And the question is, why is the EIC important, and what extra information will it give us? Alex, you're on.
So one of the good examples of what we can study with the EIC is a fundamental intrinsic property of subatomic particles called spin. And so when I say intrinsic, I mean something kind of like mass. So mass is intrinsic to a particle. It's something that it possesses. Spin is also one of these intrinsic properties that we've observed in subatomic particles. And the proton, being made of quarks and gluons, actually has kind of a complicated spin structure that we don't fully understand. So we don't fully understand why the proton has the particular spin value that it has. Originally, it was thought that it would just be coming from the quarks that would provide the spin, but we've actually discovered experiments at RHIC that the gluons also play a very large role in making up the total spin of the proton. And so the electron-ion collider, as one example, can help fill in our gaps in understanding of the spin of the proton by colliding beams of polarized electrons and ions, or polarized electrons and protons. And the polarization allows us to make the spins all point in one direction or another direction. That can give us a better understanding for what we have going in, and we can study different kinds of observables that are sensitive to the polarization of the initial particles to understand more about what is actually happening with the spin internal to the proton, for example. So that's one example. Another cool example that's really exciting to me is actually better understanding what the distribution of quarks and gluons looks like in a nucleus at high energy, because this has a lot of implications for the heavy ion physics we're currently doing at RHIC. And so, like we were talking about earlier, where we can go back and reuse data from a long time ago and analyze it with new understanding, I find this very exciting because measurements that we can make 10 years from now and understanding what the actual tomography, or like the actual visual look of the nucleus is as far as the quarks and gluons are concerned, we can actually reanalyze heavy ion data with a better understanding of the initial nuclei before they collide and possibly learn some very cool new physics from that. And so there's actually quite a bit that can be learned from the electron ion collider, and those are just two examples that are, I think, most exciting to me.
I think that adds to the versatility of RHIC as well as the EIC, that it not only can do all these various species that we have, but also polarized and unpolarized. I think that's another thing that makes it quite unique, that it can actually do that, which is from us, for the accelerator folks, it's not trivial to actually provide you with polarized particles and also maintain the polarization through the ramping up process that I explained earlier, or tried to, right? So it tends to get lost in the process, and we have to do a lot of things for it not to get lost. So it's...
One thing to point out, though, I think we're talking about the detectors as if they're an experiment, but it's important to remember that the collider itself is also an experiment. And what you get out of just the process of building the EIC is better ways to build colliders. And we don't necessarily know where that's going to go and how we'll use it, but we find later spin-off technologies like the NSLS, which you may have seen that summer Sunday, is an accelerator that is used to create X-rays to study all sorts of things. So what we learn from the building the collider itself is also going to teach us things that we can turn around, how to build accelerators and colliders better.
Yeah, indeed. One of my colleagues at the laboratory was involved with the electron acceleration at the light source, and he's also was a little bit involved with the electron acceleration for the EIC. So indeed, there's a crosstalk there, right? I'm also going to answer myself one of the questions that was brought up on YouTube. It was what makes RHIC different from CERN's Large Hadron Collider, and I'm just going to point out that a couple of the answers that we got from Michiko and Alex already, and Angelica explained the versatility of RHIC to be able to collide a large variety of species, Michiko was telling us, and to be able to spin or polarize the things that are collided, at least some of them. And that's what we heard from Alex and Angelica. So those are some of the main differences in addition to the energy at which the collision occurs. All right. The next question is from Umaka, I hope I pronounced that correctly, on Facebook, which is, what would you say are the main physics goals for S-Phoenix? And Christine, this is for you, and if you could make sure you remind what S-Phoenix is in case people have forgotten over the last half hour.
Yeah, so S-Phoenix is a detector that we're currently building, and it is focusing on two main types of probes, something called heavy flavor and something called jets. So these are probes which are really rare. So part of the reason why we don't have, why we're building a new detector to focus on this is because in the earlier phases of RHIC, we simply didn't get as much data as we wanted, and the earlier detectors were designed for things that were much more common. So these two probes, heavy flavor is really nice. These are very heavy quarks. And one thing that you can get out of them is that they stick together, and you can get a good measurement of the temperature by looking at when they melt. So this is somewhat like if you had some unknown, if you had water and you didn't know what temperature it was, you could stick different things into the water and see if those things melted. So you would see, for instance, that maybe a BB doesn't melt, but a stick of butter does melt. So then what you know is that the temperature of that water is somewhere between the melting point of butter and metal. And that's not a very efficient way to measure the temperature of water, but because we don't have as many, we can't stick a thermometer into the quark gluon plasma, this gives us a better handle on the temperature of the quark gluon plasma, and we'll be able to measure a lot more different types of these bound heavy heavy quark states. And then what's near and dear to my heart is jets. And you can think of this as a bit like, you have some of these quarks or gluons in the nuclei collide off of each other very, very, very strongly, and then you actually usually have back-to-back particles, and you sort of have a built-in control and a probe, and that's kind of nice. So this is sort of like if any of you are, if you want to tell the properties of some type of liquid, you can shine light through it and see how much is absorbed, and determine the properties of the liquid or what kind of liquid it is from that. And we're doing the same thing with the quark-gluon plasma, but we have to use these probes that are actually created in the collision because we can't just shine light through it because it happens too fast.
Thanks. So as Phoenix is coming up here in the short near-term future, can you explain, since these abbreviations and acronyms were thrown around all over the place, Christine, could you tell us quickly what Phoenix or S Phoenix stands for?
Oh boy. So the S Phoenix is an upgrade for the Phoenix experiment, and I am going to have to look. I should know the acronym. Pioneering High Energy Experiment. Yeah, Pioneering High Energy Nuclear Interaction Experiment, and the S originally sort of stood for super unofficially.
And Prithwish, earlier you tried to tell us a little bit about what STAR stands for. That's the experiment that's ongoing right now.
Originally, right?
Right. So solenoid tracker RHIC. So S-Phoenix would bring new capabilities, like it will have detectors that can collect data at much, much faster rates. So they are very good for detecting all those rare objects that do not normally come out of the collisions. I should also mention that STAR detector is currently running. It focuses on, like I mentioned, it focuses also on building very large acceptance detector. It can detect many particles at any time. So
the name STAR didn't have to do with stars in the sky.
Probably it did something, but STAR stands for like the way it's mostly it's a big detector that sits inside an even bigger magnet. I did have a photograph of it, but it's difficult here. And you can go online and just see that STAR is right now collecting data. It's probably stopped. Yeah, you can see the live collisions. Go to the page. These are directly live collisions that are happening right now in the STAR detector.
You're saying these are real pictures happening right now?
Yeah. These are live collisions that are happening. Yeah, we are colliding gold on gold at a very low energy. Yeah. You can log in and also watch it live. So.
That's more than you might get to see on a tour. So thank you for showing that, Prithwish. Good.
You're welcome.
Yeah. All right, let's take a break from social media for to go back to some of the true and false questions that we can try to answer. So here's a question for Christine again. This is, again, true or false, and if you're watching on social media, you can put in a T or F into the comment section and see if you can guess what the answer is going to be. So, Christine, the data that comes from ion collisions helps scientists understand the strongest force in nature. True or false?
True. So the strongest force in nature is called the strong force, and this is what binds the protons and neutrons together. It's what keeps the quarks and gluons inside of protons and neutrons, and also what keeps nucleons together. And by smashing these ions together, what we can do is that we're at least locally setting them free so that we can see how they freeze back together and try to understand how that happens much better quantitatively.
All right. Good, true. All right, next, true or false? Let's send to Angelica. We haven't heard enough from her lately. We need to hear more, Angelica.
Yes.
Physicists cool superconducting magnets at RHIC with liquid nitrogen to make strong magnetic fields that help steer the particles around the ring. True or false?
Yeah, so this is another yes and no question. Yes, in order to create those magnetic fields that we need to steer those particles on the racetrack of 3.8 kilometers only, we need strong magnets, and we need to cool them down to do this. And we don't use liquid nitrogen for it. We only use, we use liquid helium. So helium and nitrogen are gases usually, and if you cool them enough, they actually become liquids. And for liquid helium, that is a temperature of just 4 degrees Celsius away from absolute zero. Absolute zero would be when everything is frozen, no gases, no liquids, everything is frozen. That's absolute zero. And it's about minus 450 degrees Fahrenheit in that ballpark. Being German, I reserve the right to use Kelvin and Celsius for units. That was one thing that I never got used to. But I should explain why that helps at all. So superconducting magnets that we run, we cool with liquid helium. So, I made another prop. So this is a light bulb. I hope that everybody can see this. And everybody has perhaps, seen a light bulb and this kind of tiny little wire in there. So there's electric current going through that wire. And we have light bulbs in order to make light. But in the process of creating that light in the light bulb, we also warm up the light bulb. So, and that is due to something that's called resistance in the wire. The current goes through it, and it produces not only light, but also temperature. It's actually quite hot, and everybody who has ever changed a light bulb too soon after it popped will know that it's actually burning hot. So, and superconducting magnet or superconducting wires, which are actually used to form those magnets, they have no resistance whatsoever to current if they are cold enough. So, and that's actually a pretty cool thing, pun intended in this case, that we can use all of the electric current to actually make magnetic fields and to build these really, really strong magnets. And that's the reason we are doing that. The reason is not in order to save on the electricity bill, because we don't. You have seen those huge refrigerators in the movie. Operating this refrigerator is actually very costly. But we do that in order to build the strongest magnets that we could for those particles and for the racetrack that we already had from an earlier project that was actually abandoned in the 80s. And we had the RHIC and we had the tunnel, already. And so we built it in there. And that's why we do that. And again, we use liquid helium for it. And it's actually, it takes about 1 month to cool everything down, to the temperatures of liquid helium from room temperature. And the same in reverse. When we stop running, we actually take the liquid helium out and we bring it back to a factory by a truck. And it takes about 1 month before it reaches room temperature again. So it's actually a pretty slow process. Again, it's 2 rings, 3.8 kilometers long, so it's a lot of material that needs to be cooled. So I think Jean is actually gone from our feed.
Yes, I think one of the dangers of doing an online meeting. So I think Christine has offered to fill in for Jean until he's able to return to us.
So our next true or false question is, all the ions that are accelerated by Brookhaven's Collider Accelerator Complex are also collided in RHIC. Michiko, true or false?
The answer to this question is false. So, as we saw in the aerial photograph, there are a number of pre-accelerators that are used as injectors for the relativistic heavy ion collider. And in a sense, these are multi-purpose accelerators, and they can provide particles for other areas of research. So two in particular that come to mind, we have a facility dedicated to experiments done by NASA. And there we deliver lots of different ion species to allow the NASA scientists to study space radiation effects, both material as well as cellular. So, for example, it's well known that out in outer space, there's a lot of radiation, but for future space endeavors, both scientific equipment and in the future, people need to be able to survive that. So the NASA physicists study the effects of radiation on electronics using the beams provided by the RHIC pre-accelerators. We have another facility that is dedicated to a development of isotopes, specifically rare isotopes that are not naturally occurring. And this is it's a medical isotope facility, and these isotopes are then delivered to industry and universities and ultimately even hospitals for use in cancer therapy treatment, as well as in the development of diagnostics to help develop remedies and cures for cancer. About the ions in RHIC, we touched upon this earlier, but to give some numerical perspective. So we saw in the video these balls that represented a conceptual view of an ion. In reality, these balls, we call them bunches. We generate up to about 100 bunches per accelerator. So we have 100 bunches circulating in one direction, 100 in the other. And each bunch, which can be, depending on the species, it can be up to a meter long, but they're very, very, very small transversely. So I think Angelica mentioned that the density is very high. So transversely, the sizes are about on the width of a hair. So imagine you have two long counter-rotating noodles, and each one of these bunches has got up to, for protons, 1 trillion bunches contained in there. And while that sounds like a huge number, 1 trillion protons colliding against 1 trillion protons, the fact is that even despite the small dimensions, the density is quite low. So we are happy if we get per two opposing bunches passing through one another, if we get an interaction that is then logged by and studied by the STAR detector, or in the future also the S-Phoenix detector. So no, not all ions generated by the facilities, what was the question, are used or collide, not all of them, for those reasons.
Maybe we should add that at the LHC that was brought up earlier, asking what the difference is. They have bunches that are so dense that they actually have several collisions in one crossing of these two clouds, that not only one pair, collides, but there could even be up to 3 or so, in one crossing. Is a challenge for the detectors to keep all this separate and analyze that data, which at RHIC we typically, it's a very, very rare thing that does happen every once in a while, but it's, not a real problem. Hello, Gene, you're back.
Yeah, hopefully. That's one of the dangers of doing virtual, right? So my entire house got disconnected from the internet for a little bit there. So not just my computer.
So maybe I'll just do the next question to give Jean a chance to settle in. So the particle tracks we see in images from RHIC collisions are the result of Einstein's famous equation E = mc squared. True or false? Prithwish?
Yeah, I'm here. So it's a true statement. But before I go to Einstein's equation, I want to tell you something. Do all of you know that Einstein lived on Long Island in 1939? That place is very close to Brookhaven National Lab. It's in Catchog. Yeah, I can see you, Alex. Anyway, the house is still there.
Show this again. I didn't see. I missed it.
Yeah.
Okay.
He still lives here.
Okay. He still lives here. Yeah.
Good to know.
Every time the collision happens, this is a picture of a single collision. Can you all see this? Okay. So this is one single collision image taken by the star detector, right? So when the ions are smashed, a lot of energy is deposited in a very small region of space. So energy can be converted into mass according to Einstein's famous equation of special theory of relativity is equal to mc squared. That is, mass is energy. This is a fundamental principle of physics. A typical ion at RHIC would deposit enough energy that can produce, let's say, if my maths are right, it's 40,000 new protons can be produced according to E is equal to mc square. But that's not the important thing. This is only half of the story. The most interesting part is that what will be produced in that collision. So even if energy is available to create mass, what kind of object will be created, how many of them will be created, it is determined by another fundamental law of physics, which is the quantum mechanics. And here, when we do the collisions at RHIC, our main purpose is actually to understand the details of that quantum mechanics that governs the particle production. And believe me, there are always surprises about what will be produced. And we keep looking for new phenomena. That's one of the major goals that excites me.
Good to hear about your passion for this. It's good.
Thank you, Gene.
All right. Thank you, Christine, for picking up for me while I was absent there. All right. I believe the next question that we have is for Michiko. Can you tell us about... no, actually, we already did that one. I see now. It's for Alex. So will the EIC, when it's completed, be the only polarized electron-ion collider in the world? The only one?
Yes, it will be. So that is actually true. We talked a little bit about this earlier. So currently, RHIC can already provide polarized beams of protons, which is already, as Angelica described earlier, very challenging experimentally. We had to develop actually quite a few new pieces of technology to allow this to happen. And for the electron-ion collider, the same thing will be true because we want to have even more highly polarized beams of both electrons and also of protons and ions. And this will be a significant challenge to do. But the important thing about actually polarizing these ions, as we talked about earlier, is that in order to study this fundamental property of subatomic particles called spin, having control over the initial spin of the particles, so we know exactly to some degree what those spins were before the collisions took place, will help us better understand what we observe when the collision provides all these particles in our giant detector to take pictures of. And so having a polarized collider is very important, and the EIC will be the only one in the world when it turns on sometime down the road.
Yeah, a unique facility here on Long Island. Great. All right, I think perhaps we've been in the Q&A here for about an hour, and it's about time to wrap up. So I want to say a big thank you for all you panelists again for joining us today and taking your time and sharing with us some of the interesting facts and knowledge that we have and what's going to go forward here at Brookhaven National Laboratory. So thank you again. Another set of thank yous also to all the people out there who have joined in on the various platforms that we've been streaming on. It's great to have you participating and sending in questions, and hopefully you tried your hand at the true and false yourself. We do hope that next year perhaps we'll get to see some of you at the facility. We'll see how things go, right? But we always do hope that people do get to come in and see the facilities for themselves and see the work that we're doing. So while we are glad for the chance to be able to share with you online, we also hope that we have an opportunity to share with you in person. So again, thank you, everyone, and I hope people have enjoyed this. And so let's all say a round of goodbyes, and take care, everybody. Goodbye.